This is the solution of question 1 of homework 6. In the question we have a joint density function fxy of x comma y equal to 1 plus xy by a, where the PDF is defined in the region mod x less than 1 and mod y less than 1. Otherwise it is 0. So first we have to find a. For that, the total probability or the total probability is equal to 1. So we use the property in the double integral running from minus infinity to infinity fxy of x comma y dx dy equal to 1. So substituting the respective limits, we get double integral minus 1 to 1 plus xy by a dx dy equal to 1. So calculating this integral, we get a equal to 4. So fxy of x comma y is 1 plus xy by 4. Now we have to find whether we have to check whether x and y are independent or not. So two random variables x and y are said to be independent if the product of their marginal densities is equal to the joint density. So if simply fxy of x comma y is equal to fx of x into fy of y, then x and y are said to be independent. So let's find the marginals first. So fx of x is, we integrate out y from the joint density. So integral minus 1 to 1 fxy of x comma y dy. So integral of minus 1 to 1 plus xy by 4 dy. So this integral, after calculating, we get the x and minus x by 2 and x by 2 get cancelled. So this is a constant. Fx of x is equal to 1 by 2, which is a constant in the region mod x less than 1. And similarly for the joint density of y, similarly for the marginal y, we have fy of y is integrating out x from the joint density, integral minus 1 to 1 plus xy by 4 dx. Similar to fx of x, here y cancel out, plus y by 2 minus 1 by 2, and we get a constant 1 by 2 in the region mod y less than 1. So here fx of x and fy of y are constants, but the joint density has 1 plus xy by 4, both x and y. So here the product of the marginals is not equal to the joint density, so therefore the random variables x and y are not independent. Now to check whether they are uncorrelated or not. So the two random variables x and y are uncorrelated if the expected value of xy is equal to the product of expected value of x and expected value of y, which is expected value of xy equal to expected value of x into expected value of y. So first let's calculate the expected value of x. We already have the marginal of x, so integral minus infinity to infinity x into fx of x dx. Substituting the appropriate limits, and fx of x is 1 by 2, so this integral comes out to be 0. Similarly for y, since x and y are similar densities, you get expected value of y also to be 0. Now expected value of xy is double integral minus infinity to infinity xy into joint density of xy of x comma y dx dy. Substituting the limits and the density function, we get, solving this integral, we get a non-zero number which is 1 by 9. So here the product of these two expected values is not equal to this, therefore x and y are not uncorrelated. Now we have to find the joint density of x square and y square. Let us take z equal to x square and w equal to y square. So z equal to x square has two solutions, x1 equal to root z and x2 equal to minus root z. Similarly, w equal to y square has two roots, which is y1 equal to root w and y2 equal to minus root w. So using the fundamental theorem, we can find the joint density of random variable zw from the joint density of xy. So fzw of z comma w is sum of all with all the solutions sigma I running from 1 to 2. Here we have two roots, so the modulus of the Jacobian times the times the joint density of xy with at xy, x1 and y1, which are the roots, respective roots. So here we have two roots for x and two roots for y, so there are four combinations combinations are possible for x and y. So first let's take a look at the Jacobian. The Jacobian of z comma w is dou x by dou z. The determinant dou x by dou z, dou x by dou w, dou y by dou z, and dou y by dou w. Substituting x equal root z and y equal root w, and differentiating, we get, since x doesn't have y, sorry, z does not have any y terms and w does not have any x terms, you get 0 here. So this product, the determinant is 1 by 4 root zw. So substituting them in the formula, we get, so here the Jacobian is a absolute. So first here we have two roots of x and two roots of y. There are four combinations possible, which are x1 equal to root z and y1 equal to root w, which is the first one, and x1 equal to x2 equal to minus root z and y2 equal to minus root w, and similarly minus root z root w and root z and minus root w. So for each case the Jacobian is the same, which is 1 by 4 root zw, because we take the absolute value of the Jacobian. So we take this out as common. So 1 by 4 root zw times the sum of these densities. So substituting z equal to x, substituting x equal root z and root w respectively for the densities in the joint density of xy, which is 1 plus xy by 4. We cancel out the zw terms, and sum of 1 by 4, sorry, 4 times 1 by 4 becomes 1. So the joint density of z and w comes out to be 1 by 4 root zw for mod z, so for z in the region 0 to 1 and w in the region 0 to 1. So initially x was in the region minus 1 to 1, therefore x square will be in the region 0 to 1. Similarly w is also in the region 0 to 1. So we have to find whether z and w are independent. So first let's take a look at the marginals. So fz of z is integrating out w from the joint density, and so the change in the limit 0 to 1, 1 by 4 root zw. This integral comes out to be 1 by 2 root z. Now for the marginal of w, we get fw of w is integrating out z from the joint density of zw, integral 0 to 1, 1 by 4 root zw dz, which comes out to be 1 by 2 root w. So over here we have the product of the marginals equal to the joint density of z and w. Therefore here z and w, which are x square and y square, are independent, even though x and y are not independent.